In a real transformer featuring a delta secondary configuration, the current does not divide equally among the three secondary windings when a single load is connected across one of these windings. This unequal current distribution arises from the internal reactances inherent to each winding. The internal reactance of a winding stems from leakage flux, a phenomenon occurring when current flows. Leakage flux represents the magnetic flux that fails to link all turns of the winding. The magnitude of this leakage flux exhibits a direct proportionality to the current traversing the winding. Furthermore, the internal reactance of a winding is also proportional to the number of turns within that winding. A greater number of turns leads to a corresponding increase in leakage flux. In a delta secondary arrangement, the three windings are interconnected in a series configuration. This series connection mandates that the current flowing through each winding is identical. However, the internal reactance values of each winding can vary. Such variations in internal reactance can lead to disparities in voltage across each winding. The winding exhibiting the highest internal reactance will manifest the highest voltage across its terminals. This elevation in voltage is a consequence of the voltage drop induced by the internal reactance of the winding. The connected load will preferentially draw current from the winding characterized by the highest voltage. This preference stems from the principle that current seeks the path of least resistance. Consequently, current distribution among the three windings is inversely proportional to their respective internal reactances. The winding with the highest internal reactance will carry the least amount of current. In practical transformers, the internal reactances of the windings are seldom perfectly equal. This inequality results in an imbalanced current sharing scenario among the three secondary windings. Consider a transformer with a delta-connected secondary winding. A load is connected across one of the windings. Because this is a real transformer, not an ideal transformer, there is internal impedance in each of the three windings. The amount of current in each winding depends on the impedance of each of the three windings. In an ideal transformer, the secondary current divides equally between the windings. Because this is a real transformer, the secondary current does not divide equally between the windings. The difference between a real transformer and an ideal transformer is the impedance in each winding. If the impedance in each of the three windings is the same, then the current will divide equally between the three windings. However, in a real transformer, the impedance in each winding is not the same. Therefore, the current will not divide equally between the three windings. The current in each winding will be inversely proportional to the impedance of the winding. The winding with the highest impedance will have the lowest current. The winding with the lowest impedance will have the highest current. To further illustrate this, let's consider a practical example. Imagine a delta Y transformer utilized in a commercial building to step down the voltage from 480 volts to 208/120 volts. The delta side is connected to the 480 volt supply. The secondary, which is the Y side, provides 208 volts phase to phase and 120 volts phase to neutral. Now consider a scenario where a large motor is connected to one of the phases of the 208/120 volt Y secondary. This motor constitutes a significant load on that particular phase. The current drawn by the motor will reflect back to the delta-connected primary, and the current distribution in the delta windings will be affected by the impedance characteristics of each winding. Due to manufacturing tolerances and variations in winding geometry, the impedance of each winding in the delta primary will not be exactly the same. One winding might have slightly higher resistance, while another might have a slightly higher inductance. These differences, however small, will influence how the current from the motor load is distributed among the three delta windings. The winding that is magnetically coupled closest to the loaded secondary phase will carry a larger portion of the current, while the other two windings will carry less current. The exact amount of current in each winding will depend on the specific impedance values of each winding and the magnitude of the motor load. In a balanced three-phase system, the currents in each phase are ideally 120 degrees apart. However, with a single-phase load on the secondary, the currents in the delta primary windings will no longer be perfectly balanced. This imbalance can lead to increased losses in the transformer and potentially reduce its overall efficiency. Furthermore, the unequal current distribution can cause uneven heating within the transformer core and windings, potentially shortening its lifespan. To mitigate these effects, it is crucial to ensure that loads are distributed as evenly as possible across all three phases of the secondary winding. This practice helps to minimize current imbalances in the delta primary and promote more efficient and reliable transformer operation. Moreover, regular monitoring of transformer temperature and current levels can help detect any signs of overloading or imbalance, allowing for timely corrective actions to be taken. To elaborate on the concept of internal reactance, consider that it's not just a theoretical value, it has practical implications for transformer design and operation. The internal reactance, often referred to as leakage reactance, is a consequence of the fact that not all the magnetic flux produced by one winding links perfectly with the other winding. This leakage flux creates a self-inductance within each winding, which opposes changes in current flow. The magnitude of this leakage reactance depends on several factors, including the geometry of the windings, the spacing between them, and the permeability of the core material. In transformer design, engineers carefully consider the leakage reactance to achieve desired performance characteristics. For example, a higher leakage reactance can limit fault currents and provide better short-circuit protection, but it can also lead to increased voltage drop under load and reduced voltage regulation. Conversely, a lower leakage reactance can improve voltage regulation and efficiency, but it may also increase the risk of damage from fault currents. The internal reactance of a transformer winding can be modeled as an inductor in series with the winding's resistance. This series combination forms the winding's impedance, which determines how much current will flow through the winding for a given voltage. In a delta-connected winding, the total impedance seen by the load is a combination of the impedances of all three windings. However, since the windings are connected in a closed loop, the current distribution is not simply determined by the individual impedances of each winding. Instead, the current distribution is governed by the loop impedance of the delta circuit, which takes into account the mutual inductances between the windings. The mutual inductance between two windings is a measure of how much the magnetic flux produced by one winding links with the other winding. A higher mutual inductance means that a larger portion of the flux from one winding links with the other winding, and vice versa. In a delta-connected winding, the mutual inductances between the windings can significantly affect the current distribution. If one winding has a significantly higher mutual inductance with the other two windings, it will tend to carry a larger portion of the current. Conversely, if one winding has a significantly lower mutual inductance with the other two windings, it will tend to carry a smaller portion of the current. The mutual inductances between the windings depend on the geometry of the windings and the permeability of the core material. In transformer design, engineers carefully control the geometry of the windings to achieve desired mutual inductance values. For example, interleaving the windings can increase the mutual inductance, while separating the windings can decrease the mutual inductance. In addition to the internal reactance and mutual inductances, the resistance of the windings also plays a role in the current distribution. The resistance of a winding is a measure of how much it opposes the flow of current. A higher resistance means that a larger voltage drop will occur across the winding for a given current. In a delta-connected winding, the resistance of each winding contributes to the overall loop impedance. The winding with the highest resistance will tend to carry a smaller portion of the current, while the winding with the lowest resistance will tend to carry a larger portion of the current. The resistance of a winding depends on the material of the winding conductor, the length of the winding conductor, and the cross-sectional area of the winding conductor. In transformer design, engineers carefully select the material and dimensions of the winding conductors to achieve desired resistance values. In summary, the current distribution in a delta-connected winding is a complex phenomenon that depends on the internal reactances, mutual inductances, and resistances of the windings. These parameters are carefully considered in transformer design to achieve desired performance characteristics. In practical applications, it is important to ensure that loads are distributed as evenly as possible across all three phases of the secondary winding to minimize current imbalances in the delta primary and promote more efficient and reliable transformer operation. Understanding the internal reactances of transformer windings is crucial for analyzing and troubleshooting various power system issues. For instance, consider a scenario where a transformer is experiencing excessive heating. One potential cause of this heating could be an unequal distribution of current among the delta-connected primary windings, as we've discussed. By measuring the current in each winding, it's possible to identify if an imbalance exists. If an imbalance is detected, further investigation is needed to determine the root cause. This could involve examining the transformer's internal connections, checking for any signs of winding damage, or even performing more sophisticated tests to measure the winding impedances. Another application of understanding internal reactance is in the analysis of transformer inrush current. When a transformer is initially energized, it can draw a very large current, known as inrush current. This inrush current is caused by the sudden change in magnetic flux in the transformer core. The magnitude and duration of the inrush current depend on several factors, including the transformer's internal reactance, the voltage at the time of energization, and the core's residual flux. A higher internal reactance will tend to limit the inrush current, while a lower internal reactance will allow a larger inrush current to flow. Understanding the transformer's internal reactance is therefore essential for designing appropriate protection schemes to prevent damage from inrush currents. Furthermore, the internal reactance of a transformer can also affect its ability to supply reactive power. Reactive power is a type of electrical power that is required by inductive loads, such as motors and transformers, to establish and maintain magnetic fields. Transformers with lower internal reactances are generally better at supplying reactive power than transformers with higher internal reactances. This is because a lower internal reactance allows the transformer to respond more quickly to changes in load demand, which is important for maintaining voltage stability in the power system. In addition to these applications, understanding internal reactance is also important for modeling transformers in power system simulation software. Accurate transformer models are essential for performing load flow studies, short circuit studies, and other types of power system analysis. These models must accurately represent the transformer's internal reactance, as well as other key parameters such as its turns ratio, core losses, and winding resistances. By incorporating accurate transformer models into power system simulations, engineers can gain valuable insights into the behavior of the power system under various operating conditions and can make informed decisions about system design and operation. In conclusion, the internal reactance of transformer windings is a fundamental parameter that affects many aspects of transformer performance and operation. A thorough understanding of internal reactance is essential for electrical engineers and technicians who work with transformers and power systems. This understanding enables them to analyze and troubleshoot various power system issues, design appropriate protection schemes, and model transformers accurately in power system simulations. Remember that while the concept of internal reactance might seem abstract, it has very real-world implications for the reliability and efficiency of electrical power systems. The careful design and operation of transformers, taking into account their internal reactances, are crucial for ensuring a stable and dependable power supply for homes, businesses, and industries. Consider also the impact of transformer selection. Different transformer designs will exhibit varying levels of internal reactance. For instance, a distribution transformer used to step down voltage for residential use will typically have a different internal reactance compared to a large power transformer used in a substation. The choice of transformer will depend on the specific application and the desired performance characteristics. For applications where voltage regulation is critical, a transformer with a lower internal reactance might be preferred. However, for applications where short-circuit protection is more important, a transformer with a higher internal reactance might be a better choice. Furthermore, the operating temperature of a transformer can also affect its internal reactance. As the temperature of the windings increases, the resistance also increases. This increase in resistance can affect the overall impedance of the windings and, consequently, the current distribution in the delta-connected primary. Therefore, it is important to monitor the operating temperature of transformers and ensure that they are operating within their specified temperature limits. Exceeding these limits can lead to premature aging of the transformer and potentially catastrophic failure. In addition to temperature, other factors such as harmonics can also affect the performance of transformers. Harmonics are unwanted frequencies that are superimposed on the fundamental power frequency. These harmonics can cause increased losses in the transformer core and windings, as well as voltage distortion in the power system. Transformers with higher internal reactances are generally less susceptible to the effects of harmonics than transformers with lower internal reactances. However, it is still important to mitigate harmonics in the power system to prevent damage to transformers and other electrical equipment. There are several techniques that can be used to mitigate harmonics, including the use of harmonic filters, tuned reactors, and active power filters. These devices can selectively filter out unwanted harmonics, thereby improving the quality of the power supply and protecting sensitive equipment. Finally, it is worth noting that the internal reactance of a transformer can change over time due to aging and degradation of the insulation. As the insulation deteriorates, the leakage flux paths can change, which can affect the internal reactance. Therefore, it is important to perform regular maintenance and testing of transformers to detect any signs of insulation degradation and to take corrective actions before a major failure occurs. Common maintenance procedures include visual inspections, insulation resistance tests, turns ratio tests, and oil analysis. These tests can help to identify potential problems and ensure the continued reliable operation of transformers.